Hi guys, I found this little GIF here of elliptical orbits, and one of the things I want to talk about here, I mean, obviously dealing with astrophysics and outer space and orbital motion and things, we're going to get something called an eccentricity. And the eccentricity of an ellipse is basically a measure of ovalness. Kind of a weird word, but it's going to be a number between 0 and 1 that measures how circular or how non-circular an orbit is, a path is. So a lot of people like to think that why we have winter and summer is because we're closer to the sun in the summer and we're further away from it in the winter, but that's not actually true. The eccentricity of Earth is almost like the orange one, almost circular. We're pretty close to a circle as we go around the sun. So it has to do with the tilt of the axis and that sort of thing, and you can take physics to learn more about that. But this idea of eccentricity I did want to talk about. So we can find eccentricity. I'm going to switch it over to note. There it is. Eccentricity is just this number like I was talking about. We can find it by doing C divided by A. And remember we talked about for an ellipse, C will always be smaller than A. A is the major axis, goes all the way across. C are the distance between the foci, so that it's going to be less. So that's why this is always going to give us a fraction, something between 0 and 1. Okay? If it's 0, then that's a perfect circle. I feel like Earth is 0.98 or something, if I remember correctly, but we're pretty close to a circle. All right, so we got that out of the way. A little physics, a little astrophysics here in the morning. That's great. Let's move on to the last the last example of the day. Example 4 will look like this. So far, I've given you guys the equations, and you've kind of dissected them. And just like with parabolas, we have to be able to go backwards. So here's some information. The vertices, the actual vertices of this ellipse are at 2, 0, and 2, 4. And the foci are located at 2, 1, and 2, 3. I want you to find and write the equation in standard form for this ellipse. You can go ahead and hit pause, come back, and then we'll see how this works. I'll give you your stamp, and then we're rolling. We're on to the next one. There's only one after this. After ellipses is hyperbolas, and then we're done. Okay? Pause. Unpause. I think a great idea to start with, and some of you that I worked with so far, you've seen this from me. I like to draw sketches. So the first thing I did was just draw a little picture of what was given to me. So I have those vertices that are on top of each other. That's already telling me this is going to be an up and down ellipse, if you will. The major axis will be vertical. Then I also have the foci that lie along that same line. So we have it here. We have those points 2, 0, and 2, 4 are my vertices. So 2, 0, 2, 4. Right off the bat, if I'm going to write the equation of this ellipse, I should probably find h and k, which is the center. That's always going to be halfway between these and halfway between these if we want. But either way, 2, 2, that's going to be the center of our ellipse, h and k. So I can start to fill in things that I know. So 2k, hk. So me personally, I didn't do this on the notes, but I should have. It's going to be x minus 2 squared over something plus y minus 2 squared over something equals 1. And now we need to figure out what these somethings are. We actually know one of them already. We know that the major axis is going up and down, so that's going to be underneath the y. And then the distance from the center of my ellipse to one of these vertices, one of these vertex, is actually a. And then I can just put a squared where it belongs. So at 2, 2, and this thing is 2, 4, this distance from here to here is 2. That would be my a. And then if I square that, I would get 4. Again, I'm putting it underneath the y because it's up and down. Okay? That's kind of why we started with the graphing one. If we understand the graphing one, the rest of these kind of fall into place for us. So the last thing we need then, I need to figure out what b squared is. I don't know anything about the co-vertices right now. I don't know anything about the left and right. Does it go here, here, here? There's a bunch of different possibilities. But based on where the foci are, we can kind of figure it out. We can figure it out. So again, what was the one equation we had that relates A, B, and C? Because right now I have A. A is the distance from here to here, 2. And I actually have C. C is the distance from the center to a foci. That would just be 1. So we have A and C, and we can work around it and find B, and we use the anti-Pythagorean theorem, the fake Pythagorean theorem. So here's what we have so far. We handled all that. We've talked about why our C value is 1. Now we have our fake Pythagorean theorem, a squared minus b squared equals c squared. We know a squared is 4. We know c squared is 1. We can just do some rearranging and figure out what b squared is. B squared is 3. Now, we actually don't need to take the square root of this thing because in our formula, what goes underneath here is b squared. It's 3. Awesome. B squared is 3. That's what goes right there. So we put a 3 right there, and we're dancing. That's it. We're dealing with ellipses, right? These are just x being squared and y being squared, different values in front of them. We have standard form. We have the major axis. We have the minor axis. We have the foci. Here is the stamp I would like you to try, some different smatterings of problems. Again, I will stamp it when we finally meet face-to-face next week when we're all quarantined and hopefully free of the coronavirus. But I'll take a look then. Bring your questions to me either in office hours today or send me emails or whatever you need to do to make it happen. Wait until Monday. I don't really want you to, but if you have to, you have to. All right? Moving on.